Hello there. Today the time has come for us to start off our new technique, that is odd and even powers. Odd and even powers is a technique of integration where we look at powers of sine functions and cosine functions. And strictly to start with, we are going to focus on to odd powers. Odd powers follow the sequence to mention. They follow the sequence 1, 3, 5, 7, 9, and so on. However, to conveniently handle the section, we normally look at 1, 3, and 5. And given the fact that at that point one would have grasped the concept at hand, we focus on to those first 3. And it gives you the general approach. Even if you want to handle a power 9, a power 7, the choice remains yours as long as you get how the first 3 are handled. Odd and even powers. The first one to look at are the odd in particular. Now, under odd powers, I want to mention that we have sine of an angle say theta, cos of an angle say theta. We have things like tan. Why tan is normally mentioned when I'm handling this? It's because tan is related to cos and sine in the fact that tan is the ratio of sine to cos. And the other terms like cot, which is cos over sine, which is a reciprocal of tan. Now, generally, for power 1, I'm going to handle power by power. For power 1, to start with, I want to mention power 1. For power 1, as the first position in the sequence, I want us to look at the integral of sine of a multiple of the angle as k d theta. I want us to recall the derivatives as I'm writing. Recall the derivative of sine, recall the derivative of cos, the cosine of theta. Its integral will be generated from the derivative. After all, the original or the previous concept or technique we have just handled was function and derivative. So think about these derivatives. The other one is the integral of a tangent of an angle multiplied by any constant. Those are like general cases, but they help us handle a power 1 in that case. Now, sine of k theta, k is any constant. You have to recall that when you differentiate sine, you get cos, a positive cos. That means the integral of sine must be the cosine function, but also checking the cosine function in reverse. When differentiating, we normally put out that constant inside the angle for trig ratio. I'm being a bit slow such that someone gets the order of trig ratios as far as differentiation and integration is concerned, since we have just started involving them. Now, when you're integrating a sine, you get a negative cos of the multiple of the angle k times that angle divided by that multiple of the angle plus c. Remember, if you don't have limits. Why am I putting a negative on cos? The reason is simple. When you differentiate cos, you get a negative sign. So the negative sign is cleared by that negative put before the cos. Point of emphasis, the integral of a sine function is a negative cos. However, the multiple of the angle must be put with respect as a divisor, because when someone is differentiating, it will be seen out. So for them to cancel and one goes back. So for the cos, it will be a positive sign. After all, the derivative of sine is a positive cos divided by k plus a constant of integration in that pattern. Now, when you reach the ratio situation, that is tan, you have to recall first. You're not integrating without recalling that this is sine k theta divided by cos k theta d theta. And then when you come to these ratios, you check the derivative of a function, which is the numerator. But when it is in ratio form, think about the previous technique we have just done where we looked at natural logarithms. So the derivative of cos is sine. But when you differentiate a cos, you get a negative sign. So I'm forced to write this as negative into negative sine k theta out of cos k theta d theta. And then I involve the k. And this becomes negative 1 over k. The derivative of the denominator is the numerator, which will be cos of the denominator, natural log of the denominator plus a constant without limits. These initial stages, I've handled them as a subsection for power 1. But I want someone to have it in mind that we have already started off with odd powers, in particular power 1. But these general cases help us throughout the whole section of odd powers. Now, for example, to brainstorm this, for example, one can say, one can say find the integral of sine 2 theta d theta. The integral of sine 2 theta is now easy to handle when someone is aware that the integral of sine is negative cos. Remember, we have just deduced. So the integral of sine 2 theta, my k is 2. This will be negative cos, my k is 2, divided by the 2 plus a constant. The integral of sine 2x plus 3, it doesn't matter. Even if inside there you have added another constant, this will be negative cos of that quantity inside 2x plus 3 divided by the multiple of the angle. The angle is x, its multiple is 2 plus a constant. Now, even if someone says it is the integral of sine a half x minus 3 over 2, it may not matter which angle is involved, as long as you know the concept as we have deduced it. This will be negative cos of a half x minus 3 over 2 divided by the coefficient of the angle, or the derivative of the angle, as some scholars say. This is the same as negative 2 cos of a half x minus 3 over 2 plus a constant c as the integral. So whoever is watching this episode, I must emphasize that when obtaining these integrals, you must reflect to the power 1 technique. Which power 1 technique? I've given you all the details. I've given the details here. Now, even if it is a cos, even if it's a tan, these concepts hold. Someone can still be given to find the integral of cos 1 over 3 theta d theta. Power 1, remember, we under power 1 odd case. This will be sine of a third theta divided by a third plus a constant, which becomes 3 sine a third theta plus a constant. Very important. And you notice that I want to emphasize that dividing by a fraction a third, we take its reciprocal for it to become a coefficient 3. That should not let you off. 5. This is the integral of cos negative 2 theta plus 4 d theta. The integral will be given by, of course, when you differentiate cos, you get sine, but negative. So this will be the sine of sine of negative 2 theta plus 4 divided by the coefficient of the angle, which is negative 2, which is a negative 2 plus a c. And this brings us back to a negative 1 over 2, the sine of negative 2 theta plus 4 plus a constant. And when someone tries to reverse, it's very important at the beginning to show you the reverse processes. When you differentiate in the derivative of the angle will be a negative 2. The negative 2 clears the positive, the negative will have to give us a positive. The derivative of sine is cos, and you're back there. Now, having looked at the different cases under power 1, or what we call the general cases of sine, cos, and tan, we want to still look at the special case. The special case still under power 1, I want us to look at the factor formulae case of odd powers, factor formulae case, where we need to know that the sine of A plus the sine of B is equal to the sine of A plus B out of 2 multiplied by the cos of A minus B out of 2. Our interest under integration is the reverse process. If someone makes the product of a sine and a cos, when sine has the bigger angle, then add the sines. Similarly, when you meet the sine of A minus the sine of B, then you get 2 the cos of A plus B divided by 2 multiplied by the sine of A minus B over 2. Remember, I emphasize we are going to strictly look at that reverse process. We are given a product when the cos and sine are all to power 1, and we need to reverse such that we are able to integrate. In the same case, we can have cos of A plus cos B. Sum of coses gives us 2 cos A plus B out of 2 multiplied by cos A minus B out of 2, and the cos A minus cos B results into a negative 2 sine of A plus B out of 2, the sine of A minus B out of 2. All of those are used in the reverse process. And what do we put interest on? We are interested in one meeting sine P multiplied by the sine of Q. Consider a situation when P is greater than Q. Cos P multiplied by cos Q, strictly still when P is greater than Q. Someone to shift from a product to a sum or difference. That quality technique helps you to handle a variety of cases. Now, the question is, what do you depend on to shift from the product to a sum or difference of cosines or sines? One, you must know that when adding sines, the sine has the bigger angle than a cosine in the product. When subtracting sines, the cosine has the bigger angle than a sine function in the product. When adding cosines, it will be a cos, which doesn't matter whether one is a bigger angle or smaller angle. When subtracting sines, it still doesn't matter in the product of sines which one has a bigger angle and a smaller angle. But when subtracting cosines, you must notice that you have a product of sine functions. When adding cosines, you have a product of cosine functions. In our examples, I want to take you through directly into the examples. Okay. Integrate. part A. Integrate part A. 2 sine 5x cos 3x dx, a cosine cos 3x dx. Now when you look at this question, you will notice that I have a product of a sine and a cos. Sine has 5x, cos has 3x. There is a 2 before. That demonstrates that case number 1, where we have 2 sine cos, but sine with a bigger angle. So in reverse, you have to add. In reverse, you have to add. So this is the same as the integral of sine of 5x plus 3x plus sine of 5x minus 3x as the resultant case where the two were obtained from. This gives us sine 8x plus sine 2x and all of it with respect to dx. Remember, in the beginning I demonstrated what we get when we integrate a sine. The integral of sine gives us a negative cos of that angle divided by the multiple of the angle plus a negative cos of 2x divided by 2, and that gives us the answer as that. Part B. Integrate cos of a half theta multiplied by cos of 5 over 2 theta d theta. Now, when you're careful with reference to our cases there, a product of coses calls for addition of cosines. A product of coses calls for addition of cosines. However, in factor formulae, as I've recalled for you, I've emphasized that in front of the product there must be a 2. Just like in part A, the 2 was already in play. Now, when you meet a case, dear student, when you meet a case when the 2 is not there, then you know that your resultant sum or difference must have a half before it. How does a half come about? We generate the 2 of interest. We say this is the same as a half, the integral of 2, the cos of a half and 5 over 2. 5 over 2 is bigger. Since it's a product, I bring that first, the theta. Now this demonstrates clearly what was done to the 2 cosines to get this when the 2 is generated. Then reverse as wanted. This is the same as 2 a half, the integral of the first cosine will be the sum, 5 over 2 plus a half theta, plus the other cosine will be the difference, 5 over 2 minus a half. Each of them has a coefficient theta on it. Remember to show what you're respecting when integrating. This is the same as a half, the integral of, in particular, this is cos of 6 over 2, that is 3 theta, and here I have 4 over 2, which is 2 theta, the theta. Then integrate, that will be a half, the integral of, when you integrate a cos, you get a positive sign. Remember, as we started, remember to divide by the coefficient of the angle, plus sine of 2 theta. Remember to divide by the coefficient of the angle, and then get back the constant of integration. This time around we have a constant outside the bracket. Feel free, if you don't mind, you can feel free to get the LCM for cases of simplification, which is 6, which will give us a 2 sine 3 theta plus a 3 sine 2 theta plus a constant. Now the 6 and the 2 multiply to end us at 1 over 12 into 2 sine 3 theta plus 3 sine 2 theta plus a constant as the solution. Now, dear candidates or learners out there, I want to give you a case when we are told to evaluate. When we are told to evaluate, let's call it an evaluation question. Evaluate. Evaluate. Or question number 2. Evaluate. Evaluate part A. When you're told to evaluate limits from 0 to pi by 4 of sine 3 theta, sine 5 theta, d theta. B. You can be told to evaluate the integral from pi by 6 to pi by 3 over 2 sine 3x cos 2x dx. I want to talk about the two situations. I want to talk about the two situations before I deal with one of them. In part A, of course, don't forget that to evaluate, you must have the answer as a constant, or your final answer must be regarded as the area under the curve that demonstrates that part. Now, in part A, we have a sine, which communicates that originally one subtracted the cosines. And when we have a sine cos, with the sine having the bigger angle, it demonstrates that one subtracted sines. Now, in part A, I want to deal with part A, pi by 4 of sine 3 theta, sine 5 theta. For one to reverse, all the powers, remember, power 1, we on power 1. For one to reverse, then you must endure to bring in the 2. Bring the sine 5 theta first with a bigger angle, preferably to conveniently handle the problem. Now, in that situation, you have it as it is supposed to look like. How did someone reach this? The person had a subtraction of cosines. It's the only case when we have a sine. And when we subtracted cosines, we had a negative 2 before. So I'm going to put a negative before. So we'll have a negative a half. The integral of cos of the sum of the angles 5 theta plus 3 theta gives me 8 theta. Remember, it must be subtraction. Subtract with the cos 5 theta minus 3 theta gives me a 2 theta in that situation. Now, this recalls back. This recalls back what was done to get that product. When you subtract the coses, you get a product of sines, but with a negative before the sign, the product of the sines. So we are left with the integrating, but of course don't forget that we are integrating from 0 to pi by 4. From 0 to pi by 4. Now negative 1 over 2, when you integrate a cos, you get a positive sign. Sine 8 theta divided by 8 minus sine 2 theta divided by 2. The limits are 0 to pi by 4. Then insert limits, negative 1 over 2 into, when you insert limits, you have sine of 8 times pi by 4. 8 times pi by 4 inside that angle over 8, that is the upper limit alone, minus the sine of 2 times pi by 4 divided by 2. That's the upper limit, remember. For the lower limit, we are easily telling that it will be a 0, because the sine of anything multiplied by 0 will be 0, yet the sine of 0 is as well 0. So this leaves me with negative a half into, this is 2 sine of 2 pi out of 8 minus, this is sine of pi by 2 out of 2. At hand, that is the statement we have. That is the statement we have. Look at it keenly and see how we get our evaluation statement. That is the statement. We have negative a half into sine. If you're careful, sine 2 pi is looked at as sine of 360. Pi is 180 times 2. You get 360. Sine pi by 2 is looked at sine 90 degrees over 2. From radians to degrees, feel free. Even if you don't change, as long as at the back of your mind you know that 360 is 2 pi and 90 is pi by 2. Sine 360 is 0 divided by 8 minus sine 90, which is 1. So resultantly I have negative a half into, this is 0 minus a half, giving me another negative a half. Resultantly I get 1 over 4 as the evaluation. Therefore, the integral from 0 to pi by 4 of sine 3 theta sine 5 theta, the theta gives me a quarter, 1 out of 4, as the area under that curve. Dear students, as we have got the area under this curve or the evaluation statement as a quarter, I leave you with the part B, where you're supposed to evaluate for me from pi by 6 to pi by 3, a product of a sine and a cos, where sine has the bigger angle, cos has the smaller angle. And in our next episode, I'm going to demonstrate for you how we deal with cases when the power is not 1, when the odd power is not 1, where you must keep on set with the function and derivative cases, and you should recall the identities. So we are dealing with the 3, power 3, power 5 onwards as the very crucial now odd powers. Commonest odd power cases 3, 5 onwards. And in this we must keep on set the three fundamental identities. The 3 fundamental identities of trigonometry, or what many scholars call the Pythagorean theorem identities. So keep on set for the next episode. Thanks for watching. Follow us on our Facebook page and YouTube channel, and please subscribe.